Good morning, I'm Marco Guarnieri and today I'm presenting our work on hardware-software contracts for secure speculation. This is a joint work with Boris Kopp from Microsoft Research, Jan Reinecke from Saarland University and Pepe Vila from Imdea Software, and the paper will appear at S&P 2021. Speculative execution attacks such as Spectre exploit speculative execution, an optimization implemented in modern CPUs to leak sensitive information. Since the discovery of Spectre, researchers have been working on countermeasures to mitigate speculative execution attacks. And this is a collection of a few recent mechanisms for secure speculation. Let's start by looking at a few examples. This is a standard Spectre v1 snippet. When executing the branch instruction, the processor might speculate on the branch outcome and continue the execution based on this speculation. For instance, if X is out of bound, the processor might anyway speculatively execute the memory accesses, which results in leaking an arbitrary memory location, pointed by A of X here, through the data cache. Existing hardware countermeasures implement different ways of blocking such a leak. For instance, load delays countermeasures, such as those proposed by Sakalis and others at ISCA 2019, prevent the leak by delaying the first load until the branch instruction is resolved. In contrast, hardware taint tracking approaches taint the result of the first memory access and delay the second one, thereby preventing the transmission, namely the encoding into the cache of the information. Consider now this slightly different example. Here, the first load happens non-speculatively. Now, the first two countermeasures still prevent the leak, since they delay the execution of the second load. However, taint tracking-based countermeasures, like NDA and STT, do not prevent this leak. Why? Well, the first memory access is not tainted, since it is not transient, and so we do not delay the second memory access, which then leaks the information. So, as these examples have shown, existing countermeasures provide different security guarantees. In this talk, I'm going to focus on two main questions. First, what are the security properties enforced by hardware countermeasures? This is often not precisely stated in papers, and therefore we lack a way of assessing and comparing guarantees provided by different countermeasures. The second question is, how can programmers leverage the guarantees provided by hardware countermeasures to build secure end-to-end systems? As I've shown before, different countermeasures might allow different classes of leaks, and understanding these differences is essential to write secure programs. To provide a basis for answering these questions, we developed the framework for expressing hardware-software contracts for side-channel free programming. In our framework, a contract specifies which program executions a side-channel adversary can distinguish by observing the microarchitectural state. Contracts have multiple goals. First, they capture security guarantees of hardware in a simple, mechanism-independent manner. Second, they can be used to distribute security obligations between hardware and software. And finally, contracts act as a basis for principal secure programming. That is, they enable understanding how to securely program different platforms. Let's go into the details. Our framework consists of three main components. First, we have an ISA language describing a program's architectural behavior. The language is the standard assembly-style language, and states of the ISA language consist of memories M and register assignment A. The architectural semantics is defined by the blue arrow here, and it describes how the state is modified during the computation. This semantics is standard. Instructions are executed sequentially in order, one after the other. Second, we need a model of the hardware microarchitecture. I'll give more details on this later. For now, we just need two concepts. First, hardware state consists of architectural state sigma extended with a microarchitectural state mu that describes the state of microarchitectural components such as caches, branch predictors, and so on. The second point is that we have a hardware semantics, represented by the red arrow here, that describes how hardware states are modified during the computation. Finally, we have an adversary model that specifies which microarchitectural components, such as caches or branch predictor states, are observable through side channels. We capture this adversary model using microarchitectural traces. A microarchitectural trace is a sequence of parts of the microarchitectural state during the execution. Concretely, we consider an attacker that can observe almost the entire microarchitectural state, and details on this are available in the paper. A contract is formalized in terms of a labeled ISA semantics, where steps in the semantics are associated with observations tau that expose security-relevant microarchitectural events. Given a program P and an architectural state sigma, we have contract traces, that is, the sequence of observations associated with executing P on sigma according to the contract. Contract traces capture which executions or architectural states are guaranteed to be indistinguishable to an attacker when run on an hardware that satisfies the contract. This is formalized as follows. We say that the hardware trace semantics satisfies a contract if for all programs P and states sigma sigma prime, whenever the contract produces the same traces, then the corresponding hardware traces, that is, the sequences of portions of microarchitectural states, must be the same as well. We are now ready to present our contracts for secure speculation. Our contracts are defined in terms of an execution mode, which describes how programs are executed, and an observer mode, which describes what kind of information a contract exposes during an execution. As execution mode, we consider a sec mode, where programs are executed sequentially, that is, in the standard way, and a spec mode, where program execution also explores mispredicted paths, therefore exposing the effects of transient execution. As observer mode, which describes what information is disclosed during the execution, we consider three variants. The PC mode discloses changes to the program counter during the execution. The CT mode additionally discloses the addresses of memory operations, and it captures the standard constant time observer often used when reasoning about the absence of side channels in cryptographic code. Finally, the ARC mode additionally discloses the values loaded from memory, and as a result, this mode effectively discloses the values of all registers during the execution. By combining all these models, we can get several different contracts, which are depicted here. In our framework, contracts can be compared in terms of the security guarantees they offer to software. Intuitively, a contract is stronger than another if it guarantees to leak less information to a side channel adversary. Therefore, all contracts can be arranged in a lattice. Here we have an arrow from a contract C to a contract C prime if C prime is stronger than C. Therefore, this picture illustrates the relation between secure speculation contracts. For instance, this is a bottom contract that leaks everything and provides no security guarantees. In contrast, the top contract here is the one that leaks nothing. This is associated with an ideal processor that does not leak any information through side channels. This contract is the one associated with the SEC and CT mode, that is, the usual constant time model, and it leaks the addresses of non-speculative load, stores, and instruction fetches. The SEC ARC contract, which additionally leaks the loaded values, provide weaker guarantees, as represented by the arrow here. Similarly, the spec city contract down here, which leaks addresses of non-speculative and speculative load, store, and instruction fetches, also provides weaker guarantees. However, the sec arc and the spec city contracts are incomparable in terms of leaks, that is, none leaks more than the other. As I'll show you now, this family of contracts and their relationship illustrated in the lattice allows us to compare guarantees provided by different hardware defenses. Let's now look at the hardware side. As a basis for our analysis of hardware-level countermeasures, we developed the formal model of a simple processor. The processor supports both speculative and out-of-order execution. It has a three-stage pipeline with fetch, execute, and retire stages, and it is parametric in the branch prediction strategy as well as in the memory hierarchy, for instance, in the replacement policy used in caches. Concretely, we formalize the behavior of this processor as an operational semantics, the red arrow here, which describes how the processor state changes in response of events, such as the activation of some pipeline stage. On top of this model, we implemented several hardware-level countermeasures and we studied their security. In the following, I will explain these results using concrete examples. The first countermeasure we analyzed is completely disabling speculative and out-of-order execution. In this case, the processor executes instructions sequentially. Each instruction is fetch, execute, and retire before moving to the next one. And obviously, this countermeasure prevents all speculative leaks. The second countermeasure that we analyze is the eager delay of speculative loads proposed by Sakalis and others at ISCA 2019. This countermeasure delay loads until all sources of speculations are resolved. We formalize this by modifying our semantics to execute load operations only if all prior branch instructions in the reorder buffer have been resolved. So, what are the guarantees offered by eager load delay? In the standard spectral example, the memory accesses are delayed until the branch instruction is resolved. Therefore, there is no speculative leak. However, consider a variant where we first access a of x and then use the retrieved value as part of a control flow statement. This can potentially leak the value of a of x through control flow. The execution of the second branch instruction is not delayed since the eager delay countermeasure applies only to data loads. Therefore, we leak the value of a of x. For instance, skip is loaded into the instruction cache only if a of x is equal to 0 in this case. In general, the countermeasure successfully blocks speculative leaks involving load operation, but it does not block speculative leaks through the control flow operations. Finally, we analyzed hardware taint tracking mechanisms like STD and NDA. These mechanisms taint all speculatively loaded data as unsafe. They propagate taint through the computation, that is, they track whether we derive information based on tainted data, and whenever operations are no longer transient, the taint is removed. Finally, these mechanisms selectively delay tainted operation to avoid leaks. So a disclaimer here, STD and NDA differ in a few aspects. Notably, STD delays instructions that transmit tainted data, whereas NDA prevents the propagation of tainted data. However, they both follow this general pattern I just mentioned, and in our work we model taint tracking approaches, both STD and NDA, on top of our semantics. Again, what are the guarantees? Let's look at a few examples. Again, for the standard spectral snippet, the mechanism tags Z, the result of the first memory access is unsafe, and therefore the second memory access is delayed since Z is unsafe until the taint is downgraded to safe, that is, when the branch instruction gets resolved. Therefore, there are no speculative leaks for both STD and NDA. Consider, however, the variant that I've shown you at the beginning of this talk, where the first memory access happens before the branch instruction. Here, Z is tagged as safe, since the load is not transient, and therefore neither NDA nor STT delay the second memory access. Therefore, we speculatively leak A of x. So, while both countermeasures are effective at preventing speculative leaks of speculatively accessed data, they fail in preventing speculative leaks of non-transiently accessed information. So, that's the high-level overview of our results using examples. In the paper, we present formal models capturing these three classes of countermeasures, and we formalize their security guarantees. We do this by proving that countermeasures satisfy different contracts. Concretely, the sec countermeasure, which disables speculative and out-of-order execution, satisfies the strong sec_cd contract, which discloses program counter and addresses of load and store operations over non-speculative executions. The load delay countermeasure, which delays speculative loads, satisfies the weaker sec_arc and sec_spec_cd contracts. The latter effectively captures that load delay does not block speculative leaks through control flow operations. Finally, taint tracking mechanisms like STD and NDA satisfy the sec_arc and spec_cd contracts. These mechanisms, in practice, might leak non-transiently loaded data as captured by the two contracts here. So, our contracts and their relations allows us to give precise security guarantees for existing countermeasures and to order the provided guarantees. Disabling speculative execution provides stronger guarantees than eager load delay, which in turn provides stronger guarantees than hardware-based taint tracking solutions. As I said before, contracts provide a basis for secure programming and for leveraging the security guarantees provided by different classes of hardware countermeasures, and let's look a bit more into that. As a foundation of our secure programming framework, we rely on the notion of non-interference with respect to a given contract. A program is non-interferent with respect to a contract and the policy, which specifies what data are secret, if architectural states that are equivalent with respect to the policy produce the same contract traces. This non-interference notion can be immediately connected to hardware. If a program is non-interferent with respect to a contract and hardware satisfies the contract, then the program is non-interferent with respect to the hardware trace semantics. In the following, we consider two flavors of secure programming. First, we consider a constant time scenario where the goal is ensuring that the benign program does not leak confidential data to a side-channel adversary. Second, we consider a sandboxing scenario where the goal is to prevent a potentially malicious program from accessing confidential data outside of its sandbox. We now show how contracts can be used for both of these scenarios. Traditional constant time is a coding discipline where secrets shouldn't influence control flow and memory accesses. In our framework, traditional constant time corresponds to non-interference with respect to the SecCity contract. More generally, we can define a general constant time notion that corresponds to non-interference with respect to a given contract. That is, general constant time ensures that secrets do not influence contract observations which capture security-relevant events. For sandboxing, we say that the program is traditionally sandboxed if it never accesses information out of the sandbox. This can be modeled in our framework as first, labeling all memory out of the sandbox as high, and second, requiring non-interference with respect to the secarch contract. Since secarch contract exposes also the values of memory loads, any load from high location would violate non-interference. Again, reasoning about sandboxing on speculative out-of-order processor requires going beyond traditional sandboxing. And in particular, we have a general sandboxing notion with respect to the contract that requires both traditional sandboxing as well as non-interference with respect to the contract. This again ensures that the sandbox program cannot infer secret information, namely information out of the sandbox, from the microarchitectural state. Now we have new secure programming notions. So how can we check them with respect to the contracts we discussed before? For general constant time and the SecCity contract, one simply needs to check traditional constant time using existing tools. For the secarch contract, one would have to ensure that no secret information is ever loaded from memory, since loaded values are part of the contract's observations. So effectively, the secarch contract is useless for constant time programming. Finally, for the SpecCity contract, one can check constant time by checking traditional constant time together with a property called speculative non-interference, which we introduced in a paper at SMP 2020. For sandboxing, one would have to check only traditional sandboxing for the SecCity and the secarch contracts. In contrast, one would additionally have to check a variant of speculative non-interference for the SpecCity contract. What does this tell us? Consider, for instance, taint tracking approaches like NDA and STT. These approaches satisfy the secarch and SpecCity contracts. These mechanisms are well suited for sandboxing, in the sense that all traditionally sandboxed programs are automatically secure when we deploy these countermeasures. However, they are not enough for constant time. Indeed, traditional constant time programs would have to satisfy further constraints to satisfy general constant timeness. In the paper, we show how existing tools can be repurposed to check these general constant time and sandboxing properties. So, to conclude, I presented a framework for expressing hardware software contracts. I illustrated how the framework can be instantiated to talk about secure speculation. I then showed how to use the framework to characterize and compare the guarantees provided by a class of hardware-level countermeasures for secure speculation. And finally, I discussed how the framework enables hardware-software co-design and have shown how it can be used to automatically reason about different flavors of secure programming by leveraging existing tools. Thanks for your attention, and if you're interested in more information, the paper is here.